All right, guys, so this is going to be our FRQs notes for dealing with area and volume questions. When we reviewed it last week, it was kind of a rough point, so I hope that this kind of smooths things over a little bit. Just so you guys know, for all these area and volume questions, we have to keep in mind these first couple of points here. You need to be aware whether you're integrating with respect to y or x. If you're integrating with respect to with respect to y, then your functions need to be in terms of y, and your limits of integration will also be y values. So let me give you an example of what I mean there. So if we are integrating with respect to y, then what goes in here should be some function that has a y in it, for instance, like e to the y plus 3y. Also, the numbers that go here are y values. These are the limits of integration, okay? So that would be an example of integrating with respect to y. Likewise, if you're integrating with respect to x, then the limits will be x values, and then you should have an equation with x in here, and this should be a dx. So keep that in mind. There's ways to tell whether you're integrating with respect to y or x as you're working on the problems. For area problems, it could be that they tell you to integrate to the x-axis, the y-axis, or the functions that they give you just may be written that way. If you're doing cross-section problems, if it says perpendicular to the x-axis, then that means it's a dx problem. If it says perpendicular to the y-axis, that means it's a dy problem, and so on and so forth. So there's ways to tell for each problem whether you're integrating with respect to x or y. The next thing is the limits of integration. Now, sometimes you can have two functions that you want to find the area between them. So let's say I had these two functions, and I want to find the area between them from here to here. Well, the functions are not intersecting at all. They don't touch. I just want to go from A to B, and for those types of problems, they'll tell you what A and B are. They'll say, find the area on the interval from 5 to 9 or something like that. Now, if they don't say explicitly what the limits of integration are, it's probably because the functions intersect. So if you have two functions that actually intersect with each other, then the limits will be where they're crossing, because usually the way they word the question is find the area that is bound between the two curves, which implies that you're looking for where the curves are crossing. So those are two things to keep in mind with all of these problems that we're going to be looking at today. All right, so we have three types of questions, okay? We have area questions, we have cross-section volume questions. The key word here is cross-sections. That, if you see that key word, then you're dealing with a cross-section problem. The disk method or washer method, the key word to look for there is the word revolution. If you guys see the word revolution or revolves around or something about revolving, that's your key word that indicates that you're going to be doing one of these two things. Okay, the difference between the disk method and the washer method is as follows. The disk method has one function and one axis, whereas the washer method has two functions and one axis. So that is the four types of problems that we will be seeing with the area and volume type questions. So what I'm going to do is I'm going to do a variety of exercises from old FRQ questions. I'll probably do about 8 questions, and I'll just kind of show you how to use this reference sheet to figure out where to go and what to do with each one. And then I'll assign you guys after this some practice problems that kind of match the ones that I did. And once again, I'm just going to be sticking to the really basic ideas. They can add some little twists and turns with these types of questions, but I'm going to be sticking with the basic ideas in this particular lesson. All right, so let's begin here. All right, guys, so you can either write this down by hand or you can just look in your blue books. In the blue books, it's FRQ 2005, and it's going to be pretty close to page number 2. It just depends on what FRQ book you have, but it'll be pretty close to that page if it's not the right page. You'll also want to notice that this is question 1, and therefore that means this is a calculator-based question. Anytime a question is either 1 or 2, then it's a calculator-based question. All right, so let's take a moment and read through this, and then we'll do number 1, part A. Let f and g be the functions given here. Let R be this region here, and S is this region here. Our first question is asking to find the area of R. So I want to find what is the area of this little triangular-ish area here. Okay, that's my goal. Well, let's go ahead and take a look at our options. Now, the first thing that we should be noticing is that we're being asked about area. So we're in this process here in one of these. Now, am I being asked to find an area between one function and the x-axis? So in other words, like say the x-axis is this horizontal line and here's a function, and I'm being asked to find the area here between the function and the x-axis? No, that's not what this problem is. Am I being asked to find area to the y-axis with one function? So in other words, like let's say I have a function that looks like this, and I want to find the area to the y-axis like this. How much area is between the function and the y-axis. This problem, actually, the one that we're doing right now, can be thought of in that way. I wouldn't recommend going in that particular route with it, but because we don't have just one function here, we're actually dealing with 2 functions. From here to here, we're dealing with one function. You could find the area that way to the y-axis. But for the rest of it, you'd have to find the area to the other function, because after that point, they split. So you could do that, but you'd have to set up 2 separate integrals to do it. I wouldn't recommend it. I think the best one that this fits is going to be the area between 2 functions. And so when I'm looking at this, I see a function that is on the top here, and I see a function that's on the bottom, and R is the area between those 2 functions. That makes more sense to me. And so that's the route I'm going to go with on this. So now we have to ask ourselves, we have 2 options. If this is the area between 2 functions, am I doing this with respect to x or y, and how do I know? Well, let's take a look. My functions are all in terms of x, so this must be a dx problem. So we're ready to go ahead and begin the integral. So according to the steps here, if I'm doing a dx type of problem, then, let me highlight it real quick, we're doing this one here, then that means I need to identify my starting point where the area begins, my ending point where the area begins, keeping in mind these are x values. We need to do the top function minus the bottom function. All right, so we'll keep all of that in mind as we're working on this. All right, so for the first problem here then, the top function would be this purple one, which is the g function. The bottom function would be this green one here, which would be the f function. And so I've got my setup there. It's going to be top minus bottom, so it's going to be g minus f. Now, where are we integrating to and from? Well, we start here on the left at x equals 0, and we end our integration here where they cross, and we have to find that point on our calculator, and that's an intersection point. Okay, so at this point, I'll just kind of verbally state what we should be doing. You're going to graph the 2 functions that they've given you down here, and you're going to find where they intersect, and you're going to put the x value of that intersection here. So you might want to pause the video and give that a try, and when you unpause it, I'll have my solution up and available. So I get about 0.178 for that x value of their intersection there. And then from there, we're just going to type this thing into our calculator. So let's go ahead and do that. Once again, I would recommend typing in the f function as, you know, your y1, I'd type in your g function as your y2, and then I would do the integral with the y1 and y2 here rather than trying to type the whole functions into the integral itself. Also, when you found your intersection point, the best way to do this would be to store it as alpha a right after you found the intersection point. The way you do that is by pushing enter after you find the intersection point. Then you push the STO button on the left side of your calculator, and then you click alpha, and you click any one of the green letters that are available, A through Z, and it will store it as that letter, and that way you could just type that letter in instead of typing in a rounded value. If you are going to type in a rounded value, I would go to the fourth number after the decimal, the 10,000th place, just to make sure that your final answer is correct to the third. All right. So anyway, if you need to do that, pause the video here and give it a try. When you unpause it, I'll have the answer for you. All right, guys, and there's your answer. Now, how would they have graded this FRQ? They would have given 1 point for finding the intersection. They would have given 1 point for setting up the integral correctly. And they would have given 1 point for finding the final answer there. Okay, so that's a 3-point question there. It's a little generous, honestly. I don't know if they usually give that many points for that type of question, but that's how they did it this particular year. I'm going to skip part B because it's a little bit redundant. It's the same type of thing, but it'd be a good question to practice, so maybe that'll be one of the practice questions I give you. Let's go ahead and take a look at the volume of the solid when it's S, the region S, is revolved about the horizontal line y equals 1. Well, now whenever I hear the word revolved, that makes me think either disk method or washer method. Okay, so now the only difference between those, as I mentioned, is that the disk method involves only one function, whereas the washer method involves two. So let's go back and take a look at our picture here and see what we're looking at. So we're revolving this about the line y equals -1, they say. So I'll go ahead and I'll just draw a horizontal line. That'll be somewhere down here. So there's my axis of revolution that I'm going to be revolving it around this. Okay, but as you guys can see here, we do have two separate functions. I've got the S function here. I'm sorry, not the S, the F. And then I have the G function here. So I've got two functions that I'm rotating around that pink axis down there. And therefore, this is going to be a washer method type of question. So now we want to decide, you know, which function is farthest from the axis. Which function is farthest from the axis? Let me bring that stuff back that I had sketched earlier. Here's my axis, and then we have the f function on top, and then we have the g function on the bottom. Now, which line is closer to the pink axis of revolution? Is the green one farther away from it, or is the pink one farther away? Well, the green one seems to be farther away from this axis than the pink one. Okay. That's going to, the one that's farthest away from the axis, that's going to help us find our big radius. So I'll just draw a line here. You don't have to draw this on yours, but that's going to be the big radius. Whenever I rotate this green shape around the pink axis, that's going to trace out a really big circle. Whereas whenever I am rotating it, the distance from the pink line from the G function to the axis of rotation, that's a smaller radius. So it's going to trace out a smaller circle as we go. Okay, so now the next question is, are we doing a horizontal axis of revolution or are we doing a vertical? Well, we graphed it earlier. It was a horizontal axis. And since it's a horizontal axis, we're going to be following these steps. So the big radius is the function that's farthest away minus the axis. The little radius is the function that's closer to the axis minus the axis. And then we're going to put the big radius here we're going to put the little radius here, and our limits of integration are going to be x values, starting from the left and ending on the right. So let's go ahead and put that stuff to work here. So my big radius we decided was this one. It was farther away from the axis down here. And so my big radius is equal to the f function minus the axis, which is -1. Now we can just simplify that as f plus 1. The little radius is the distance of the g function to the axis. So that's going to be the g function minus the axis is going to be g plus 1. So my big R is f plus 1, my little r is g plus 1, and so according to the washer method, the volume that would form as I rotated these would be the big radius minus the little radius. And we're doing this with respect to x, and I need to find my limits of integration. Now I already found them earlier, well at least I found this one earlier. Now I need to find the other one, and that's what's going to go here and here. And remember, these are the x values of those intersection points. So let's pause the video here and see if you guys can find the intersection points. Plug them in here. Remember, it's best to store them as letters, and then that way you're not rounding. But if you do choose to just write them down, at least go out to the fourth number after the decimal so that your final answer, when you round it to the third number after the decimal, is more accurate. Okay, so when you can pause the video, I'll have the solution up here. All right, so there is the final answer in the box there, 4.558. This was another 3-point question. You would get 1 point for having this set up correctly. You would get 1 point for having the correct limits, and also 1 point for the correct answer. The pi is probably just going to be considered part of the integrand there, so that's part of that 1 point. So there you guys have it. So that's a volume question. So we did an area question, we did a volume question. Let's take a look at a couple more. All right, guys, so let's take a look at another one. This one's going to be close to page 6 on your blue books if you guys want to look at it, or if you just want to write it down. It's the 2007 question 1. I'm not going to be doing A or B just because I feel like they'd be a little bit repetitive from what we've already done in this video, but I will be doing part C. A thing to take notice of here is that this is question 1, so once again it is a calculator-based question. All right, so without any further ado, let's go ahead and read the instructions here and see what we can figure out. So let R be the region in the first and second quadrants. So we see that we're looking at an area named R, and it's in the first and second quadrants. It's bounded above by this function, and it's bounded below by this function, which is just a horizontal line. So we don't really need to graph it, I don't think, but we can. The reason you don't really need to is because they're telling you which one's on top and which one's on bottom. I guess we would actually need to graph it to find out where they're intersecting so that we know the limits of our integral. So let's go ahead and graph this up a little bit here. Let's go to our y equals. And what was my function? It was 20 over 1 plus x squared. So 20 divided by, and in my denominator I need parentheses, 1 plus x squared. And then it's bounded below by the line y equals 2. So we'll go ahead and graph it. Now they said in the first and in the second quadrants. This is kind of interesting because I only see it being in the first quadrant. Let me do a normal view on this calculator. So if you ever want to get back to a normal view, let's push zoom and then 6. And there's our fuller picture. Now they said that it was bounded below by the line y equals 2 and above by the line 20 over 1 plus x. I'm going to actually adjust my window, go a little higher because I'm thinking it probably like curves off up here somewhere, but I want to see the whole picture. Once again, I don't know how important it is to do this, but I'm just being picky here. So let's go up to 20 and see what that looks like. There we go. So what we're looking for then is we're looking for this area here. I'm not going to color in the whole thing, but you guys get the idea. So there's that. So what I would need to do is I need to find out where these things are crossing eventually, but we'll get to that. So now let's go to our little reference sheet and see how to use it. For part C, you'll notice that we're talking about cross sections. So there's one of our keywords. So we're doing one of the cross section type problems. Notice that it says perpendicular to the x-axis. That's another important keyword. And then semicircles. All those things point to how we should go about using our reference sheet. So here's our reference sheet. This is not an area question. This is a cross-section volume question. So question 1, what's the base length? Am I dealing with perpendicular to the x-axis or y-axis? Well, they said perpendicular to the x-axis, right? So I know it's not going to be this. I know it's not going to be this. So now I have to ask myself, is it one function or is it two functions? Well, on this problem, it was two functions. It was bounded above by 20 over 1 plus x squared and below by the function y equals 2. So we're going to be using this format here to find our base. So the base of the problem that we're working with right now is going to be the function above minus the function below. And there's my base. All right. The other key word that we want to look at there to help us find the correct area formula is we were dealing with semicircles. So the area formula is going to be pi over 8 times the base squared, and my base was this. All right, and then finally we're ready to find our volume, and that's basically just when we integrate the area formula we just created from A to B with respect to x, because we are doing perpendicular to the x-axis. So now that's where I need to come in and find those places where the graphs intersect each other. So let's go ahead and get back to our graph here, and we'll find these intersection points because that tells us where to start and where to stop for the area between the curves. All right, so we know how to do that. Second Calc 5. Oh, I think I pushed the wrong button. Let me try again. Second Calc 5. And we want to scroll to the intersection point and push enter 3 times. And it's -3. That's easy enough to remember, so I don't need to store it or write it down. The other one's probably +3 because this thing looks symmetrical, but just to be safe, I'll do it anyway. So I'll scroll over to the other place where they cross. Enter 3 times, and it's +3, sure enough. All right, so we now have enough information to go ahead and answer the question that has been asked of us. We are integrating from -3 to +3, pi over 8 times the base, which is 20 over 1 plus x squared minus 2 squared with respect to x. And of course, we'll punch that into our calculator and see what we get at this time. Just so you guys know, though, well, we'll look at how it's graded in a minute, but this is definitely part of the grade here is writing that little statement out. But let's go ahead and calculate it here. So I'm going to go back to my home screen. Math, 9. Actually, let me delete that. I'm going to put the pi over 8 in front first. So in parentheses, pi divided by 8. Then I'll do math 9 from -3 to +3, and it's going to be in parentheses y1 minus y2 in parentheses and square it with respect to x at the end here, and we get 268, and that's how we would write our answers right up to there, the third number after the decimal. We don't need the rest of it. Make sure you do your rounding appropriately because this was a 4. It stays as 8 here. Okay, so let's see how this thing would have been graded. So they're giving 2 points for having the proper integrand, meaning, oh, I'm looking at the wrong question. My bad. Let me clear that out of there. Here we are. You get 2 points for the proper integrand. That would be this entire piece here. That's the integrand. I'm wondering if maybe they would have given one of the points for correctly finding these points and also having the correct limit. I think that these two would be part of this 2-point process. Technically, just this piece here is the integrand, but not the limits, but I think we need to include those. So anyway, the final answer obviously is worth a point. So I would say just overall, without getting too complicated, having this whole thing set up correctly is 2 points. Having the final answer is 1 point. And that's been pretty consistent so far with a lot of the problems we've done in this video so far, is they seem to be giving 2 points for the setup and 1 point for the answer. Let's move along. Okay, the next one we're looking at is the 2009 FRQ, and it's going to be pretty close to page 10 in your FRQ notebooks, I believe. Notice it's question 4, and that's significant because this means it's a no calculator type of question. And so I'm going to be doing quite a few of these problems here, just to because each one of these will demonstrate something a little bit different. And so we're going to go ahead and do all of them on this last run through here. Let's go ahead and get started. All right, so let's read. We have the region R. They seem to call these areas R a whole lot for some reason. In the first quadrant is enclosed by the graphs of y equals 2x and the graph of y equals x squared. It's kind of important that you guys, it's not a huge deal. I think you could probably figure it out anyway, but this is the line 2x because it's a straight line. And then this is the line of x squared because it's like a parabola. Hopefully you guys know that parabola equations look like that. Straight line equations look like that. And so that way we know which one is on top and bottom, because as you guys know, that's kind of a relevant point whenever you're doing these questions. It says find the area of R. So let's go ahead and take a look at our reference sheet here for this. This is an area question. So now, am I finding the area between one curve and the x-axis? No. Am I finding the area from one curve to the y-axis? No, I don't think we're doing that either. Are we finding the area between two curves? Yes, we are. Now, are we doing this with respect to x or with respect to y? Well, the functions they gave us look like this. And so I don't see any reason why we can't just do this with respect to x. So I think that's going to be a good approach to go with. I'm not a big fan of doing things with respect to y unless I have to. So we're going to go with respect to x. However, just so you guys know, it is technically possible to do this with respect to y. I just prefer the x method. So we need to find where the functions intersect, because the problem doesn't tell us what the limits are. It's going to be top minus bottom. Okay? And that's pretty much it. Now down here it says if the functions intersect more than once, you'll need to set up multiple integrals for each area region. But in this problem, you know, the graph looks like this. So there's only one area region. It's not like they're intersecting twice, creating two separate regions. So there we go. So we're just going to be using this little basic format here. So let's get back to the original problem. So we know the setup's going to look like this. Intersection point 1, intersection point 2. It's going to be the top function minus the bottom function, and then dx. Okay, the top function is the yellow one, so that's 2x. The bottom function is the x squared, so we'll put that there. So really all I need to do is just find the limits. And that's actually pretty simple, because usually what you'd have to do is you'd have to set these equal to each other and solve. But that's kind of easy. I'm still going to do the work just to demonstrate it, but the reason it's easy is because you could see where they intersect just by looking at the graph here. But if you had to do it by hand, you would move both things to one side. Then you would factor and set each piece equal to 0. So we have x equals 2 and x equals 0, but we could see that obviously from here. So we're going from x equals 0 to x equals 2. All right, so now that we have our setup, let's go ahead and do the integration process. I'm going to go ahead and make this look a little simpler though. All right, so step 1 is going to be to integrate. The integral of 2x is x squared. The integral of x squared is x cubed over 3. Then we're going to plug in our numbers. So if I plug in 2 here, I get 4, and plugging in 2 here, I get 8/3. Then plugging in 0, we end up with just 0, so that whole part we can just ignore. And since this is an FRQ, we don't need to simplify this. That's good enough as an answer. Okay, so that takes care of part A. Let's go ahead and move on to part B here. Actually, I think I'm going to go ahead and skip part B. It's not a bad question. It's just kind of an abnormal type of question. And so it's just going to, I want this video just to kind of be about some of the basic and most common types of questions. So we'll focus on just part C here. All right, so another solid has the same base R, so same base here. For this solid, the cross section is perpendicular to the y-axis. Okay, we got some keywords here. We have cross sections, so we know what type of problem we're doing here, cross-section problem. And it's perpendicular to the y-axis. That means we're going to be doing dy. And it says the cross sections are squares. It says right, but do not evaluate an integral expression for the volume of the solid. So let's go ahead and take a look at that. So my reference sheet, we're going to jump down to the cross section. It's perpendicular to the y-axis. So we know we're not going to be worrying about this, and we also know we're not going to be worrying about this. And we do have two functions involved here, 2x and x squared. We don't have just one, so we're not using this. So this will be my base. So now, when we look at our thing, it says we want to do the right function minus the left function. So our graph looks something like this. That's the line 2x, and then this, that's the line x squared. Which one is on the right side? This one is on the right, and that's the x squared. So that one's going to come first, but it's not going to look like that in just a minute, and you'll see why. And the 2x is the one that's on the left, okay? But here's the thing, though. Since we're doing this perpendicular to the y-axis, that means we need to be doing an integral with respect to y, which means that A, these are y values. So remember before we used 0 and 2? Well, those were the x values. But for those same points, we're going to be putting there now the y values. Another difference is we can't use these equations. We have to rewrite them so that they are equations in terms of y instead of in terms of x. So let's go ahead and start with the y equals x squared problem. Well, if I want to get the x by itself, I would square root both sides. And as you guys know, we get a plus and a minus. Since we're in the first quadrant, that's the right half of the graph, so I only care about the positive version of that. And so that is what the right function is going to be now. It's going to be square root of x. Now, let's go ahead and do the other equation, y equals 2x. If I want to get x by itself here, I would just divide. And so that's equal to y over 2. And so my left function is going to be y over 2. So if we do right minus left, we get this. And then finally, we just put the limit values in here that we need. So there's our setup. Oh, I forgot. We're doing squares, right? So that's just the base. I forgot. That's just the base. So if you want to find the area, it's the base squared. And there's nothing to multiply on the outside here. And when we integrate that, we get the volume. So let's go ahead and go back to our problem here and finish it up. All right, so my y value here is 0. My y value here is 4. And we're going to have the right function minus the left function squared dy. All right. And at this point, we could be done because it said to write the integral but don't evaluate it. And so this is our answer there. All right, so let's go ahead and see how they would have graded this FRQ. So for the first one here, where they just wanted us to find the area, you get one integral for correctly orientating the functions as top minus bottom. That's 1 point. You get 1 point for doing your antiderivative correctly. And then you get a point for your final answer, which I chose not to simplify it, but that's okay. This is what it would have been, and I didn't need to simplify it. So for part C, you get 2 points for your integrand and 1 point for your limit. So here's your integrand, so that's 2 points, and then 1 point for getting the limits correct as well. All right, so that is how those ones were graded. All right, so we've kind of gone through a variety of the more basic and fundamental types of area questions. There are, of course, some other things that they could ask, like I skipped part B because on this problem, it's a cross-section problem, but it's none of the areas that I give you where it's like the square or rectangle or anything. And this one, they just tell you what the area is. And so the difference there is that you would have to integrate, find your limits, and then you don't have to find out what the area formula is because they just give it to you. So it's actually easier if you understand what the question means, but that's the trick, is understanding what the question means. So you don't have to find the base and then do some kind of formula to it. They just give you the formula. So that's kind of nice. So there are twists and turns that they can take, but if you guys at least know the basic stuff, you've got a strong foundation to accomplish most of the important goals, and possibly, if you're ready, to go on and take higher questions on. But anyway, I'll give you guys some practice problems as well to go with these. They'll be basic like these. They'll there'll be things like finding area, cross sections using one of these things here, or washer or disk method. So they're all in there, and hopefully this was helpful to you guys, and we'll move on to our next one soon. See you then.